In class on Friday, we had a quick reminder about this other form of the chain rule. So dy dx is equal to dy du times du dx. If I want the derivative of y with respect to x, but y is not a function of x, y is a function of u instead, then I can take the derivative of y with respect to u and multiply by the derivative of u with respect to x. So we did a little bit of practice in class, kind of like filling in the blank to make sure that all the pieces of our chain in the chain rule connect. So if I had dz dx, if I wanted dz dx, but z was a function of p, I would take the derivative of z with respect to p, and then to make the pieces of the chain line up, I'm going to need to multiply by the derivative of p with respect to x. That can even work if you need 3 pieces in your chain. So if I want the derivative of p with respect to x, but p isn't a function of x, I could take the derivative of p with respect to r. Maybe r is not a function of x, so I can multiply by the derivative of r with respect to q, and then multiply by the derivative of q with respect to x. So again, we practiced taking the derivative of an expression with respect to the variable that is there, and then multiplying by the piece that we needed to fill in the blank, to connect the pieces in the chain. So recall, before we get rolling here, that if I wanted the derivative with respect to x of some function of y, let's say y cubed, y cubed is not a function of x. So if I want to take its derivative, I take the derivative with respect to the variable that's there. So the derivative of y cubed with respect to y is 3y squared. I'm going to multiply by that missing piece of the chain rule, in this case, dy dx. So we're going to need that in these few examples. So here's a relation between two variables, x squared plus y squared equals 1. It doesn't happen to be a function. This is the graph of a circle, if I wanted to graph all the ordered pairs that are solutions of this equation. It still kind of makes sense to talk about the slope of the tangent line. So that's what I want to do. I want to find a way to find dy dx, the slope of the tangent line to this curve, given an x and a y coordinate, even though I won't be able to isolate the y in this equation. So we're going to do that using what's called implicit differentiation. We're going to take the derivative of both sides of this equation with respect to x, and in places where we're taking the derivative of a piece of the equation that doesn't contain x's, we'll take the derivative with respect to the variable that is there, and then multiply by the missing piece. If the expression we're taking the derivative with respect to x of, contains y's, then we'll take the derivative with respect to y and need to multiply by that missing piece, which will be dy dx. So here we go. I'm going to take the derivative of both sides. So I can take the derivative of a sum by finding the sums of the derivatives. So the derivative of x squared plus y squared is the same as the derivative of x squared plus the derivative of y squared. Now, parts of this are super easy. The derivative with respect to x of x squared is 2x. The derivative with respect to x of 1 is 0. What am I going to do when I need to take the derivative with respect to x of y squared? I'm going to take the derivative with respect to y and then multiply by dy dx. So that's what I have here. 2y is the derivative of y squared with respect to y, and I'm going to multiply by the missing piece, dy dx. Once I've done this, once I have an equation that contains the expression dy dx, I'm hoping to isolate dy dx because that's what I want. That's what slope is here. So I'm going to do whatever algebra it takes to get dy dx by itself. In this case, let's subtract 2x and then divide through by 2y. Those 2's can cancel, and the slope is negative x over y. dy dx equals negative x over y. You've finished here when you've isolated dy dx. Notice later, if you want to find out the slope of the circle, the curve, at the place where, I don't know, some point that's on the curve, would that be radical 2 over 2 and radical 2 over 2? I could replace x with radical 2 over 2, y with radical 2 over 2, and I would be able to compute the slope. Here's the next example. I have 2y equals x squared plus sine of y. This is a relation between x and y, but I can't write it as a function of x because I can't isolate the y. There's no algebra we could do that would isolate the y. I can still find an expression for the slope of the curve, given then any input value. And I do that by using implicit differentiation. And I take the derivative of both sides of this equation with respect to x and use that version of the chain rule whenever I need to take the derivative of a piece that doesn't contain x's but contains y's instead. So the derivative with respect to x of 2y is the derivative of, with respect to y of 2y, which is 2, multiplied by the derivative of y with respect to x, dy dx. And that's going to equal the derivative with respect to x of x squared is 2x. And the derivative with respect to x of sine y, what's going to be the derivative with respect to y of sine y, which is cosine y, times the missing chain rule piece, which is dy dx. So that's what I have here. 2 dy dx is 2x plus cosine y times dy dx. And this one's a tiny bit harder than the last one because now I have dy dx in two places. And I'm trying to isolate something that shows up in two places. So our technique here is to move any term that has a dy dx factor to one side, move any term that doesn't have a dy dx factor to the other side. So that's what I've done here by subtracting cosine y dy dx. Now the technique is to factor out the dy dx. In this case, I'm factoring out on the left dy dx times 2 minus cosine y equals 2x. Now I can isolate dy dx by dividing both sides by 2 minus cosine y. So that's what I have here. Dy dx is 2x over 2 minus the cosine of y. Notice what that means. If I ever want to figure out the slope of that original curve at some place on the curve, I need both the x and the y value to substitute in to this expression. The slope of this curve depends on both the x and the y. When we had functions that were written functions of x, y is some function of x, the y was by itself on the left-hand side, then our derivative, our slope, depended only on x. But in cases where we use implicit differentiation, we might find that we have a slope expression that requires both an x and a y. All right, so there you go. There's our plan. If I need to find dy dx in a case where I have a relation between x and y, but I don't have a function, I'm going to use implicit differentiation. That's take the derivative of both sides with respect to x, and then isolate dy dx. All right, so here's another example. Find the equations of the line tangent and normal to this curve, and I've given an ordered pair. So to write the equation of a tangent line, I need a slope and an ordered pair. An ordered pair I already have. So how can I find the slope of a curve if that curve isn't a function? I'm going to use implicit differentiation. So just notice the tricky part here, the reason this example is in your notes, is because we have this application of the product rule. So x squared minus xy plus y squared equals 7. I'm going to take the derivative of both sides with respect to x. So the derivative with respect to x of x squared is 2x. That's the easy part. The derivative with respect to x of 7 is 0. That's the other easy part. The part we're kind of already getting the hang of, the derivative of y squared with respect to x, is the derivative of y squared with respect to y, which is 2y, times the missing piece of the chain rule, which is dy dx. Let's talk about what happened in the middle there. How do I take the derivative with respect to x of negative xy? I'm going to have to use the product rule. That's first times the derivative of the second plus second times the derivative of the first. Notice I'm been asked to find dy dx. So I'm taking the derivative of both sides with respect to x. So I'm going to have to take, when I use the product rule, it's going to be first times the derivative with respect to x of the second plus the second times the derivative with respect to x of the first. So that's what's happening here. A couple ways you could think about this. Just notice here I've sort of factored out that subtraction. So you see here's the subtraction, and I'm using big brackets afterward to make sure I distribute that subtraction back. So the two things getting multiplied together are x and y. So it's going to be first times the derivative of the second. Well, there's the x is the first. The derivative of y with respect to y is 1 times, I'm going to have to multiply by that missing piece of the chain rule, the dy dx. And then the second part of the product rule, so plus the second times the derivative of the first. Well, the second is y. Here's the y. The derivative of the first, the derivative of x with respect to x is 1. So that's what I have here in the middle is x dy dx plus y. You could have done it so that you thought of that subtraction as a negative x and then use negative x as your first. It's just another way to do it. Just make sure you're consistent. So if you decide to distribute the subtraction, make sure you use the brackets like I have. So now I have an equation. It has 1, 2, 3, 4 terms on one side and a 0 on the other side. I'm going to try to keep together any term that has a dy dx factor and move to the other side any term that doesn't have a dy dx. Okay, so here this is distributing that subtraction. Notice afterward I don't have the brackets left anymore. So now I'm going to move to that side, the 2x using subtraction. I'm going to add y to the other side. Those are the two terms that have no dy dx. And I'm going to leave the dy dx terms where they are. It's going to give me minus x dy dx plus 2y dy dx. The dy dx gets factored out. And then I'm going to divide both sides by 2y minus x. So here's my expression for dy dx. Y minus 2x over 2x minus y. If then I want to go back and write the equation to the line tangent, the equation for the line tangent to this curve at the place where, what is that? X is -1 and y is 2. I'm going to take this expression and replace all the y's with 2, all the x's with -1. I get 4/5. So then, once I know that, to write the tangent line equation is no problem, right? I'm going to use 4/5 as the slope. I'm going to use -1 comma positive 2 as my ordered pair. Here's the equation for the tangent line. Equation for the normal line uses the opposite reciprocal slope. Notice on the free response section, I strongly suggest you just leave your answer like that. I think you'll find that most of the time on the multiple choice section, they'll even leave the answers in point slope form for you.